So following on from the previous video, we've seen that when you differentiate 2 to the power of x, you're going to get some constant times 2 to the power of x. And when you differentiate 3 to the power of x, you're going to get some constant times 3 to the power of x. And in general, when you differentiate a to the power of x, you're going to get some constant times a to the power of x. And bear in mind that this constant here is dependent on this a here. So bear that in mind. Okay, so when you differentiate a to the power of x, you're going to get some constant, but then this constant here depends on this a here. So you can imagine it as something like this, a function of something that is dependent on a. Okay, so we've seen several times that when you differentiate a to the power of x, you're going to get some constant here times a to the power of x. And we are now at a stage where we don't fully understand this block here. We would then, at the moment we don't really understand this block here, so we would translate this whole thing here into something else. Now what I mean by translate is that we would preserve the true meaning of this but then change everything else. So when I say translate, we're going to preserve the true meaning of this, but then change the way we would visualize this whole thing here. So at the moment, we don't fully understand this block here, so we would translate this into something like this. And then, well, up here, you would take the limit as h tends to 0. But then down here, because we've translated, we are preserving the true meaning of this, but then we're just changing the way we would visualize this thing here. So we would translate this into this thing here. But then when we are in our translated form, it really means us approaching this thing here. Okay. Well, if you don't understand this bit here, watch some of the earlier videos. We've done several videos on this already. Okay. So hang on. So now so when you differentiate a to the power of x, you will get a constant times a to the power of x. We don't fully understand this thing here, so we would translate this into this. That's one way of us trying to understand this. Now here's another way of us trying to understand this. So at the moment we don't fully understand what this thing really means. So we would translate it to this, just so that we can investigate, just so that we can have a rough understanding of this thing here. So this here is one way of doing it. Now here's another way of trying to understand this. Okay, here's another way. Hang on. So when you have when you differentiate a to the power of x, you're going to get this thing here. Okay, but here's another way of trying to understand this block here. So when you have when you have y equals a to the power of x, if you differentiate it, you're going to get this thing here. Okay, so when you have this, if you differentiate it, you will get this. So this here represents a gradient of this thing here. Now, so when you have this and then you differentiate it, you will get this. Now, if you try to find the gradient at x equals 0, now if you put 0 into this thing here, so don't forget, this here is your original graph. If you differentiate it, it will give you this. Now, when you put 0 into this thing here, it means that you're working out the gradient at x equals 0. But the thing is, when you put 0 into this thing here, into the x here, when you put 0 into this x here, you're going to have this block times a to the power 0. Now, a to the power 0 is 1. So here you've got what you're trying to understand times 1. Now that's good. When you're trying to understand something, isolate it. So now we've got something that we are trying to understand here. How? So at the moment, dy by dx here. When you're trying to, at the moment, we don't really understand this block. So we are now at a stage where we've isolated what we're trying to understand. So what we're trying to understand is equal to the derivative at x equals 0. So hang on. So start again here. When originally y equals a to the power of x, when you differentiate it, you would get this. So dy by dx equals this thing here. So now find the gradient at x equals 0. So you would then put the 0 into this x here. So when you put the 0 into this x here, this thing here is going to become 1. Now 1 times this thing is just this thing here. So now you've got so basically you've got your what you're trying to understand here. So one way of interpreting this is what you're trying to understand, which is this thing here, is the gradient at x equals 0. That's what it means. So now it's good to isolate what you're trying to understand. So when you're here, you've really got a case where what you're trying to understand is on its own. What you're trying to understand is the gradient at x equals 0. So what that means is this block here. Another way of trying to understand what this block means is this. Hang on. So you've got your graph y equals a to the power of x. Now that block that we're trying to understand is really the gradient at x equals 0. So you trying to understand that complicated block here, you trying to understand this block here is really you trying to understand the gradient at x equals 0. That's just another way of trying to understand this block. So now we have two ways of understanding this block. One way was to translate it. Remember, hang on. So let's start again. We are now at a stage where we don't fully understand this block. Now, one way to understand this block is to translate into this form, which we've seen in one of the earlier videos. Now, another way of understanding this block here is really you trying to understand the gradient of y equals a to the power. So y equals a to the power of x. Another way of you trying to understand this block here is you trying to understand the gradient at x equals 0. Okay, so now we have two ways of trying to understand this thing here. The new way is you trying to understand the gradient at x equals 0. Okay.